Alright, hello everyone and welcome to the Discrete Probability lecture for Texas Financial Derivatives. Again, my name is Matt and today, as I said, we'll be talking about discrete probability. We're going to go over some things such as what a probability model is and a few examples of the most famous probability models. We're also going to talk about two statistical properties commonly associated with probability that are expected value and variance. Now that in the last lecture we talked about what probability is and how to compute it, and we also talked about what events are and what the probabilities that they occur and how they might be related if they are independent or dependent from one another. But as I said, today we're going to be talking about discrete probability, and I think before we do that I need to give you a definition of what a probability model is and what it means to be discrete. And so, a probability model is simply a mathematical function with its primary parameter being a random variable of some event x. And what it does is it will output the probability that this event occurs with some observation. And this is typically denoted as the probability of big X equals little x. I'm going to go ahead and write that down. So, a probability model is a mathematical function whose primary parameter is a random variables observation and outputs the likelihood our random variable takes on some value. This is usually denoted as the probability big X equals little x, where big X is whatever our event is and little x is some value that it can take on. And so, what we mean by discrete probability, when we say discrete, there are two types of probability. There is discrete and continuous. So what we mean by discrete probability is when our event can take on a certain finite set of observation values. For example, this can be rolls of a dice. So rolls of a dice can only be 1, 2, 3, 4, 5, or 6. We can count them and they are also integers. But it doesn't necessarily need to be integers. But most of the time, it is integers that we are using. It's whole numbers, mainly natural numbers. But a event that would not be discrete, for example, would be let's say the weight of a man or woman or whatever. You can have the weight be 160 pounds, 125.2, 163.777777. I think you get my point. There are an infinite number of values somebody's weight can be just by extending the decimal place, and this is referred to as a continuous probabilities, but that won't be until the next lecture. But for right now, we're focused on discrete probabilities. We're focused on events that have a finite set of occurrences or observations that can happen. And so, since now that we know what a probability model is, our next question is, well, how do we use it, and what probability models are out there that can model events in the real world? And for that, we will talk about our first probability model, the binomial model. Okay, So let's go ahead and write what this is. So what the binomial model is like this, like a probability model is a probability model that outputs the likelihood of a certain number of successes, and we'll talk about what, and I'll go on and say what I mean by this. Probably one that outputs the likelihood of a number of successes in n independent Bernoulli trials, where the success of each trial, where the probability of success of one trial is known, where probability of success is known and fixed. So, in order for us to know a little bit better what this means, we first need to clarify a few terms. We need to know what we mean by success. We know what we mean by Bernoulli trials, and we need to know what I mean by the probabilities being known and fixed. And so I'm going to write the definition of a Bernoulli trial down here. So when I talk about a Bernoulli trial can really be, just any type of turn-based system, or it's just a trial. It's just a go ahead. It's a run. Something's going to happen, and it's either going to be this, that, or something else. But what is important about a Bernoulli trial is that there's typically a win and a loss aspect to it. And the easiest example to understand is of a coin flip. So in a coin flip, you flip a coin, that's one trial. And depending on what you're betting on, heads or tails, there's a certain win or loss. If I say, let's flip a coin, if I get a heads, you have to buy me a soda. So then you're betting on tails. For me at least, I'm deeming getting a heads as a win, or in this case, a success. This is what I mean when I talk about a success. As for the probability part, we know what the probability is. It's a 50-50 shot. The probability I get a heads on one coin flip is 50%, the other 50% being the tails. And so this is what I mean by a Bernoulli trial, with a success and a known probability. And so I'm going to write down like a little definition of that. So it is a turn slash I guess trial is a good word. A turn slash trial with a win-loss aspect, where the probability of winning and losing are known, and then I'll say, for example, coin flip. So this is what I mean by a Bernoulli trial, and I'm going to go ahead and get a drink. All right, So, as I said earlier, the binomial model, reading this definition, it's a probability model that outputs the likelihood of a certain number of successes occurring in n independent Bernoulli trials where the probability of success is known and fixed. When we flip a coin, the probability we get a heads is 50%. If we flip the coin a second time, the probability doesn't change. It's the same coin. It's not a weighted coin. This isn't some schemy little gambling situation on the street corner that some guy's betting us and he knows something we don't, and we might win. It's known and fixed. And let's say we're playing a game where if we get 2 heads out of 3 coin flips, we win some money. Whatever amount of money that you think you would deserve out of that. But if we get 2 heads out of it, out of 3 coin flips, we win. So first off, let's just try to figure out the probability that happens before we even use a formula which I'm about to give for the binomial model. And let me go ahead and write down what this formula is. I'm going to go ahead and put it at the top, and then I'm going to show you. Actually, I'm going to go ahead and put it, since we know what a Bernoulli trial is now, I'm going to go ahead and erase this. And I'm going to say that the binomial model is mathematically given as the probability that our random variable event x is equal to some little x observation of success is equal to n choose k, okay, xer equals k, n choose k, p to the k, and then 1 minus p to the n minus k. Now, write this formula down. It's going to be very important. We're going to go ahead and show why this is true first. And we're going to go ahead and do a visual example and use this formula to show that they both that they do the exact same thing. Okay, and here, as I said, n is your number of trials. So in this case, n is going to be 3. K is going to be our number of successes. If we deem a success as being a heads, then we want 2 successes. So k is equal to 2, and p is the probability of 1/2. I'm going to go ahead and show this first. So if we have 3 coin flips, we can get tails, 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 heads, heads, heads. We can get heads, tails, tails. We can get tails, tails, heads. We can get tails, heads, tails. We can get heads, heads, tails. We can get tails, heads, heads. And we can get heads, tails, heads. And I believe that's all the possible ways. So there are 8 possible ways, this outcome with some guy on the corner can go if he bets us 2 heads out of 3 coin flips. There are 8 possible things that can happen. Out of those 8, how many ways is there for us to get 2 heads? Well, heads, heads, tails, tails, heads, 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 tails, heads. So out of these 8 possible ways, we have a probability of 3 out of 8, or 37.5%. It's not the greatest. I mean, it's something. It's over 1/3, depending on how much money we might win or lose. If he's betting us back, this may or may not be the best situation, the best game to participate in. But this is how we get the probability visually. But let's say there's 10 flips. We're not going to write out all 10 flips, or that's going to be a lot of ways that can happen. So let's use the binomial model and to do it. So I'm gonna go ahead and get rid of this I'm gonna go ahead and I'm gonna leave the formula though. So the probability that our event, if we call x the number of heads we get out of 3 coin flips, probability we get 2 heads out of 3 coin flips is going to be n, our number of trials, 3. Choose k, where k is our number of successes. P is the probability we get 1 heads in 1 trial, which is 1/2, squared, and then 1 minus 1/2 to the n minus k, which is 3 minus 2. 3 choose 2 is simply 3. It's 3 factorial over 2 factorial over 1 factorial. So this is going to be 3. 1/2 squared is 1/4. And then 1 minus 1/2 is 1/2. Raised to the 3 minus 2 is raised to the 1. And so it's just 1/2. 1/4 times 1/2 is 1/8. So we get 3 times 1/8. Look, they match. This shows you that this model is accurate and that it works. If you're curious about why it works, I'll explain this in 2 parts. So the first part, p to the k times 1 minus p to the n minus k. If I'm doing 3 coin flips and I want to figure out a way I can get 2 heads and 1 tail, well, that means I'd have to do a heads, and then a tail, or a tails, a heads, and then you get it. So if I want to get 2 heads, well, probably I get a heads is 1/2. Probably I get another 1 heads is 1/2 times that. And then probably I get a tails is the other side of that, which is still 1/2. So this is why you do p, your probability of success, do it squared, and then you have to multiply by the remaining failures that would occur. That's where this part comes from. This n choose k part is the number of ways we can rearrange two heads in 3 slots. I said 3 choose 2 is 3. Look at how many ways we can rearrange 2 heads. 1, 2, 3. That's where this comes into, and each of them are worth 1/8. So that's why we get the 3 times the 1/8. This is why this works as it does. And I'm gonna go ahead and compute the rest of it. Actually, I'm gonna leave this up for now, or no, might as well, just to show you more of this model and to show you that it adds to 100% as we would like. Probability x equals 0 is 3 choose 0. I'm gonna go fast here. 1/2 cubed, 1 minus 1/2 to the 0. 3 choose 0 is simply 1. 1/2 cubed is 1/8. So we get 1 times 1/8 is just 1/8. Any number raised to the power of 0 is 1. So we get 1/8. Probability x equals 1. So that's going to be the probability we get 0 heads, which we can see that 1/8. Only one possible occurrence. Probability x equals 1. 3 choose 1. 1/2 raised to the 1. These are backwards. 0 and then 3. 1 minus 1/2 squared. This is 3 choose 1 is 3. This 1/2 to the 1 times the 1/2 squared. That's going to give us 3/8. And the probability x equals 3. And you can see that here's 1 head, here's 1 head, here's 1 head. This is going to be 3 choose 3, 1/2 cubed, 1 minus 1/2 to the 0. We're going to get 1/8. You can see right here, 3 heads. 3 plus 1 is 4, plus 3 is 7, plus 1 is 8. So in all, we get 8 out of 8 equals 100%, which means it's valid. That shows us that our math is correct. And as I told you on the last video, all your probabilities must add to 1. Before we go on to our next thing, let me get another drink. All right. So before, I'm gonna go ahead and erase this. Before moving on to our next probability model, our last one, I want to talk about two statistical properties that are closely related with probability, and that is expected value and variance. Expected value is defined as the sum of your random variables individual observation values multiplied by their respective probabilities. I'm going to go ahead and write this out in mathematical terms. It might make a little more sense. So expected value is, it's also defined as your mean or average. These are terms you probably heard before. So I'll say is the sum of your random variables individual values multiplied by their respective probabilities. This is mathematically given as expected value of your random variable x is equal to the sum over all x, this thing means for all x, of x times probability, your random variable x equals little x. Let's compute expected value using our example. Based on our example, the expected value of x equal to the sum of our values times our respective probabilities. Well, what all values can it take on? We can get a 0, a 1, a 2, or a 3 number of heads. So that'll be 0 times the probability 0 occurs, which is 1/8, plus 1 times the probability 1 occurs, 3/8, plus 2 times the probability 2 occurs, which is 3/8, plus 3 times the probability 3 occurs, which is 1/8. 0 times 1/8 is 0. This is 3/8. 2 times 3 is 6, so it's 6/8. 3 times 1/8 is 3/8. So 3 plus 6 is 9. 9 plus 3 is 12. We get 12/8. Or dividing this by 4, we get 3/2. So what this means is if we do many trials over and over and over, we can expect on average we're going to get 1.5 heads out of 3 coin flips. Now you can't get half a heads, but this just means if you got 0 heads one time, 1 head, next time 3 heads and 2 heads and 3 heads and 2 heads and then 0 heads and 0 heads and 0 heads and 1 head. You kept going on forever. If you add them all up, divide by the number of times you did it, you would on average get 1.5 heads. Now, I'll go ahead and just leave this up. So now for the next thing, variance is another statistical property, and it is defined as your expected spread, or the amount your random variables values vary from the mean. This is very much used in stock return because we want to know how much our stock return is going to vary from its expected value, what we expect it's going to be. If it varies a lot, this isn't good for us because we don't know where it's going to end up. And so variance is the expected spread or variability within our model's values from their average output. Mathematically, I mean, it kind of makes sense if you just read it. The variance is equal to the expected value of the amount our model's values, the x, varies from the mean. This is expected value, or you can also use mu, which a lot of people use, and then this is squared. The reason we square it, and we won't have enough time to do the variance for the other one, but the reason we square it is because think about if one of your observations was less than your expected value. Like, for example, we got 1/2 for our expected value in the coin flips. A number of heads we get is less than that. But if we didn't square it, this would make it seem like we are taking away from the spread, when really we aren't. 1 minus 1/2 would be -1/2. That would tell us that there's less variability we're taking away. That's why we square it, so we can make everything positive. And then we take the standard deviation of it, which is just the square root. And that's another term you might have heard. I mean, the standard deviation is literally equal to the square root of your variance. All right. So now that we've talked about some of the statistical properties, now I'm going to try to wrap this lecture up because I think it's nearing on 30 minutes. But now that we've talked about some of the statistical properties, we're going to talk about our last discrete probability distribution, which is the Poisson distribution. It is used very, very much. I'm going to go ahead and give you the definition of it. So the Poisson distribution is a probability model that tells us the likelihood of a certain number of observations, of a number of observations occurring within a time interval given the average amount that occurs in that time interval. In that interval. And when I say average, I literally mean the expected value, because the expected value, is another name for it, is just the average. And this is given by the probability x equals little x is e to the negative lambda times lambda x over lambda to the x or x factorial, where lambda is equal to the expected value of the model. And I'm going to go ahead and give you a quick example, and then we'll wrap up. So, say you are in a grocery store and you're coming up on a line, and every 10 minutes, the average amount of customers that walk through that line is three customers. So your lambda, or your expected value, every 10 minutes is equal to 3 customers. What if you want to know the probability the line is completely empty? That you are going to walk up to the line, you're gonna go up there, and you're gonna get in and out really quick. You're not gonna have to wait at all. You might want to know the chances of that happening. Well, let's use the formula. That's gonna be e to the negative lambda, which is your expected value every 10 minutes. So that's 3 times lambda to the x, which is 0, divided by x factorial, so 0 factorial. If you use a calculator, you can easily get this. 0 factorial is 1 3 to the 0 is 1, so it's really just e to the negative 3. So it's about 4.97%. So it's not that likely to happen. Let's say you want to know if the line's going to be super busy. That might be even more important. Like, you want to know if you're going to be there for a long time. Let's say probably x equals 5. There are 5 people in that line every 10 minutes. That would be e to the negative 3 times 3 to the 5th over 5 factorial. Again, just using your calculator, you can figure this out, times 3 to the 5th over 5 factorial. This is a little higher, 10.08%. This is all I had for today for us to talk about. I hope y'all learned a lot today. We talked about what a probability model is. It's a mathematical function with the primary parameter being your random variables observation values, and it's used to figure out the likelihood your model takes on some value, or the event you are modeling. We talked about the binomial model. It's a model that outputs the likelihood of a certain number of successes occurring in n independent Bernoulli trials, and we mentioned what a Bernoulli trial is. We talked about 2 statistical properties, expected value and variance, that are used a lot, excessively. And then we talked about the Poisson distribution, which tells you the likelihood you have there are a certain number of observations within a specific time span, given the average amount that occur in that time span. So that is all we had to talk about in this lecture. To the next lecture, we're going to be talking about continuous distributions. That'll be not necessarily harder. I think it's just a little bit different mindset, but we're going to go over it very slowly and in a very good way. So I hope y'all learned something. Please remember to follow the Instagram. It's at texas.fd. Like, subscribe, and comment. Again, Austin and I, the 2 educators in this club, will make sure to get back with you and try to get some more one-on-one help, because I know some of these topics can be difficult. But all right, thank you guys.